I understand I've already said a bad word, because if there's progress, then there has to be progress toward a goal. And that was, I think, the word that elicited the first heckle this morning, on Monday morning. So I'll be talking about progress toward goals. There will be goals, but these are not going to be goals that I'm imputing to nature. Okay, I'm not suggesting that evolution has a goal. There will just be goals that I set up from time to time to analyze various situations. So the first goal I want to talk about is my goal for this talk, or at least for the subject matter that I'll be talking about in this talk. Ultimately, I'd like to be able to talk about quantitative estimates of rates of various processes. And the sort of theme of my talk is you shouldn't necessarily expect progress to be proportional to time. It might have some other functional form other than just being proportional to time. On the other hand, I don't want to lump all polynomial rates of growth into one class and be satisfied to say that that they're all equivalent to one another. And at the moment I'm in a math department. I've spent a lot of my life in computer science departments. Before that, I've worked both as a mathematician and an engineer. In computer science, there's a tradition. One of the core values is placing a high value on negative results. So this is also very common in mathematics. Proving that things cannot be done is something that seems harder and therefore more valuable than proving that something can be done. To show that something can be done, you show how to do it. To prove it can't be done, you have to consider all possible ways in which some clever person might do it and rule them all out simultaneously. So I'm a victim of this mindset as well, and so I'd like to emphasize negative results in this talk. So the first one I want to talk about is a paper by Haldane that's already been mentioned twice in this conference, and that's the title, "The Cost of Natural Selection." And it is, the tone of the paper is as a negative result. He's saying that here's a problem in the theory of evolution, and we have to somehow come to grips with it. And the conclusion he comes to in this paper is that to fix each gene in the genome, if there are some genes that you would like, or that evolution would like to bring to great prominence or even complete fixation, then it takes about some number of generations per substitution. And that's, I think, the point of the paper is that he's asserting that the number of generations you have to spend to fix n genes is somehow proportional to n. Okay. I'm not going here to flog the horse of Haldane. There are many papers that point out erroneous or limited assumptions that he's making. I want to pick up on the idea in one of these papers by Maynard Smith, and it's this notion of truncation, which appeared this morning in Manfred's talk, and carry it to what I think is its logical conclusion, and get from it a lower bound. So I don't want to worry about, whether I don't want to stop at pointing out, as Maynard Smith did, that Haldane is wrong. I want to try and find what is a valid lower bound on the number of generations you need to fix n genes. So, of course, to prove anything, I'm a mathematician, I'll need to make some assumptions. So imagine that you're a farmer, and so you have a a population of stock of some sort, and you want to fix the alleles at n particular loci to be the good thing, the thing that you want to breed them for, and they're already present at moderate amounts. There's a version of the theorem that will apply even if they're present in very tiny amounts initially. But suppose initially everything is there half and half. There are two alleles, a good one and a bad one, and the average number of the average population of each allele is a half. Okay. I'm going to make a number of assumptions, some of which are crucial and some of which I think are easily avoided. I'm going to, just for simplicity, assume it's a haploid genome. I'm going to assume no mutation occurs during the period to which this result will apply. So there are two reasons for this. One is I want to talk about the cost of natural selection, and so I want to ignore other processes that might be occurring. And I feel entitled to do this because there's a time period, time scale on which natural selection has an effect that's arguably between mutations which occur on a longer time scale. I'll assume non-overlapping generations. I think that's an innocuous assumption. It's what Haldane also assumed. So it's a discrete time process. I'll assume sexual reproduction. That will be absolutely essential, and we'll see what happens if we don't have sexual reproduction later. No assortative mating. I think that's inessential. No linkage and recombination. That will be absolutely essential. If the good genes are linked to one another, then if you get one, you get both. And so you're not going to get that sort of result. I'll assume that the fecundity of this stock is unaffected by not only the genes that the farmer is trying to fix, but also by any other genes that might inadvertently have their frequencies altered by the processes that are being undergone. And now I come to the assumptions about the farmer. I'm assuming the farmer knows not just the phenotype of each individual in the stock, but actually the genotype. So the farmer sequences each of their animals. And I'll assume that the farmer is omnipotent in deciding which animals get to reproduce. After he decides that, I should have said he or she. It used to be a program, What's My Line? And a very frequent thing they had was a woman who did something like breeding pigs. And this was hard for the panel to guess because they never guessed that a woman would be breeding pigs. But so I'm assuming that the farmer knows what the genome of each animal is and has complete control over whether it gets to reproduce or not. So complete control over its reproductive fitness, okay, and survival, of course.
Does the farmer know the fitness of all possible genomes, or any genome he sees, he has to test the fitness of that?
No, so the fitness function is the farmer. The farmer is trying to obtain a population of the same size as the original, in which these at these n loci, all the genes are good in every member of the population. Okay, and in order to do that, the farmer gets to.
The genes interact. The effects of the genes interact with each other. The fitness is not additive in the properties of the genes, or.
So
the farmer wants white, tall.
Okay. The farmer has one particular genome which he likes.
Yes.
Right?
Yeah.
Okay.
Yeah, exactly. And he wants the whole population to have, at least at those n loci, exactly what is desired.
Right.
And I'm assuming that whatever happens at other loci is not going to make his stock sterile or something like that. Okay, so what I'm assuming then is that there's a completely arbitrary map from the genotype to the phenotype, and a completely arbitrary map from the phenotype to the ability to survive and reproduce. Okay. So, of course, this is a very strong assumption, but we're trying to get a lower bound, so that makes the result all the stronger.
No, sorry, but then now I'm totally confused, because you said the fitness was just determined by the farmer. He has one genotype that he likes.
Yeah.
But now you're saying I have an arbitrary function for whether it can reproduce.
So what I'm saying is the farmer can behave in an arbitrary way. The farmer is the function that determines how
If
the
the farmer
genotype.
can do it, then neither can evolution.
Yeah.
All right?
So if
Yeah,
the farmer
I'm-
has constant selection, or limits on the selection
That's his point. If
intensity,
the farmer cannot do it,
the
then
limits
forget
on
it.
selection
Cannot be done.
intensity.
The farmer gets to completely control which stock breed.
But how many, is there a minimum number?
Okay, so I'm going to be assuming a finite but large population. Well, maybe I'll discuss this after I describe what the algorithm will be. This will be something we've also seen this morning. The farmer will choose a threshold at each stage for how many genes, on the average, are right in the current. The farmer will choose a threshold and will allow only those stock that have that fraction of the genes right, in the farmer's opinion, to breed, and the others will not be allowed to breed at all.
So I'm still totally confused. It seems at one point you said the farmer has one particular phenotype that he likes. So
Yes.
like gene A from here,
Yep.
gene K from here, gene
Yep.
R from there.
Yep.
And that's the only one he cares about. He likes that.
Right, and he doesn't have that at the beginning.
Right.
So
But
at the beginning,
then you said the ability to reproduce and all those things or some arbitrary function of all the genes.
He didn't
the
say-
farmer, that function describes the farmer's behavior.
But the farmer the farmer cares about one particular genotype and
Yeah.
everything else is bad.
Yes,
Everything else is equally bad.
that's right, but there may not even be an element of the population that has that phenotype. So at the first round,
No, I understand that, but it's not a, okay.
The farmer can sculpt the landscape to be as beneficial as possible, to evolution as quickly as possible to that peak that he wants.
Right.
I think it was being said.
yeah, thank you. I think that's,
Okay.
yeah. Okay, so the farmer is going to choose a threshold and then truncate the population to those individuals that are above the threshold, allowing them to reproduce and not allowing any others to reproduce. And then
changes.
the threshold will change from step to step. And then after, of course, culling the herd, the farmer has to let it regrow to its original size. This is exactly what Manfred
Right.
described.
So, but if one guy is perfect, has all N genes, then the game is over because you could threshold it then. And what if one guy is perfect or a small number is perfect, then you let those populate and then you grow the population from them and then you're done?
Well, that's a strategy, and that takes the number of generations that goes from, you probably need two things to be perfect, one male and one female, to the size of the original herd. And that will depend logarithmically on the
So
size of the original
okay,
herd.
got it,
But you
got
may
it.
not have that.
Yeah,
On
okay.
the average, you won't.
Okay.
Yeah, have that. So this is the basic step. You cull your stock, picking out those that are above a certain threshold in terms of the number of genes that are good, number of loci at which the gene is good, and then you breed until you've returned to the original size of your population, and then you can repeat this. So, for example, at the outset, you could set your threshold to be so initially, if everything is completely random, you have a binomial distribution. It looks like an exponential, like a normal, and so you could say I'll only breed those that are above average, And so then the average in your new population, the next generation, is going to be some fraction of a standard deviation above what the average was originally. Originally, half the genes were good in your population, and after culling and breeding, you've increased the average by a computable amount. Okay, and this is really the only thing the farmer can do. I mean, the farmer is looking at genotypes and deciding for each animal which ones to breed. And you can show that for a given reduction in, for a given number of animals that you allow to breed, you may as well pick just those that are above a threshold, because any other choice will be stochastically dominated in terms of the average level of genes by that choice. So then it's just a question of how many times do you have to raise the threshold, and how much should you raise it by each amount, and that depends on the fecundity of the stock, how much they increase by in a given generation. But this strategy is essentially optimal at raising the frequency of each good gene to being 1 minus epsilon. After that, there's a little end game that you have to play where you've got enough of the perfect stock that with a reasonable number of generations you can cull to just the perfect ones and let them expand to the size of the original herd. So the conclusion you come to is that the number of generations you need to fix n genes grows as the square root of n, and the constant depends on the fecundity, as I said before. But my point is it's not proportional to the number of genes you fix. It's proportional to the square root, and it's a lower bound. You can't fix n genes in a number of generations that's logarithmic in the number of genes you want to fix. There is some limit. It's just not a limit that's proportional to...
The population, this depends on the population size? Or?
No. I'm assuming that there's a large but finite population. I have to assume it's finite in order to talk about returning the population to the original size. If I wasn't required to return the population to the original size, then I could just go along until I had some perfect animals and then just quit there. And it's the constraint that I return to the original size that...
But also the constraint that you didn't have every possible combination in the population originally. That's also, that depends on the population size as well. If you have a big enough population, you have all combinations there originally. If the population is bigger than 2 to the little n there.
Yeah, but so the... okay, so suppose the population is large enough that I have everything there. Okay, initially everything is present with frequency 1/2. So if there are n genes I want to fix, a fraction 2 to the minus n of the population will be these perfect guys. And now to restore that to the original size, I need n doublings of the size of the population, and so I'm using n steps to do that. So even if there are some perfect things there originally, that's not the way to go. Yeah.
Beautiful.
Yeah. Unless you're lucky and there are lots of them there. Yeah.
So there is not any random step here. Everything.
Oh no! There's a random step, and that's the sexual reproduction. So the sexual reproduction.
This the farmer controls that.
No, the farmer controls which animals get to reproduce. The farmer does not get.
It doesn't rule meiosis.
Doesn't rule recombination. That's the crucial thing.
Okay.
Yeah.
Sorry.
Yeah.
Or even mating.
That gives us a next generation in which there's a binomial distribution again on each of the loci.
Nice.
So there's an interesting point about what farmers actually do. And actually the optimal strategy is to control the mating, because you have a kind of, in a finite population, you want to reduce inbreeding. And so The optimal strategy is slightly better than this if you choose the mates so as to avoid chance inbreeding. I mean, it's not a big difference.
Yeah,
it's
yeah.
a qualitative change.
I was asking Adi if he knew anything about how important this assumption was, and
Those are particularly bad things you want to avoid.
yeah,
No, it's about slowing down the loss of variation. So you're losing variation by chance exchange, and you want to slow that down. So you want to have a strategy which balances progress, which is
Independent of
Yeah.
even the very
but another way of looking at it is you want to fix the deleterious, potentially deleterious genes in a good state, and you just add them to your n, and you say you want to.
If you can see genes, that would be true.
Well, yeah, and I'm assuming the farmer can see the genes,
Right.
not just the phenotype.
Yeah, but,
so-
but by avoiding inbreeding, I mean actually avoiding reducing the variation in the trait you're looking for, which is the number of good genes.
But this exercise is an exercise in reducing variation. You have certain genes that you want to fix at particular values, and you don't care, by definition, by assumption, what happens with the other genes.
In a finite population, you might mix one of the good ones. You might lose one of the good ones because you were so busy selecting on other good ones.
Yes,
So
there.
that's conditional on you having
Well,
a great population.
that's why I'm assuming it's a large population, so that you get good approximations to the binomial
That's true, so
distribution
random
at each
mating
step.
is fine,
Yeah.
so large population.
So I missed,
Yeah.
did you say that 50% was the optimal strategy? Or was
No,
that
no,
the
no.
formula for the optimum?
No.
The threshold.
What the optimum is will depend upon fecundity and how many generations you need
Is there a
to.
simple expression for that, or is that
No.
complicated?
You know, C is going to be a complicated expression, and
Well, C is a complicated expression, but the schedule for the threshold is that complicated.
at the beginning it's not complicated.
In the
but-
end game it is?
Well, it depends upon. You see, I started out saying you want to absolutely fix these N genes. In practice, one is happy if the bad genes are only epsilon. And if they're only epsilon, then depending a bit exactly on how you measure that, what norm you put on the error vector, there will be different endgames, different ways of playing the endgame. So really what I'm talking about is just getting to the stage where all the errors are very small. And for getting a lower bound, of course, you have to get all the errors to be very small before you can get them to be
Give
perfect.
us a sense on the schedule, though, even in the early stages, then, of what the optimal truncation is?
Yeah. So you will, in the early stages, truncate so as to restore the original population in one generation. So you're making relatively small truncations. That's assuming that you're starting from a place in the middle. The process actually accelerates because even though the standard deviations are going down, the size of the standard deviation relative to the number of errors you're trying to get rid of is actually increasing. Okay, as I've argued, this is actually a lower bound. I think it's a lower bound in the sense that Haldane intended his paper to be deriving a lower bound. And my point is just that it's not proportional to the number of genes. It's proportional to something else. Sex is absolutely essential here because I'm ignoring mutation. And so the only way you can get perfect organisms if you don't have recombination is to have them present in the original population. That's the only source of randomness here. And so then, it just as in the example we went through, you need a number of generations proportional to n to amplify the perfect subpopulation to be the size of the original population. Yeah.
So your fecundity, though, so I mean, this totally agrees with like Felsenstein and Ney and Crow on the reproductive excess, fecundity being the critical part of Haldane's load. But what if yours is Malthusian, right? So there's no density dependence. It's as easy to go from half the population to full as it is to go from very small to half.
Yeah, I'm assuming there's a carrying capacity that you wouldn't go above.
But that you just multiply to get, because like in a real population, not the farmer,
Yeah,
you know, restoring the second half of the population is harder than,
Yeah.
it's usually harder than restoring the first half.
yeah. Yeah, so then there might be, you might want to initially go to a very small population, small as you could get by with.
Or a third where you're sort of in the middle of the logistic or somewhere.
Yeah.
I mean, it could change, right?
Yeah, and then at the very end, you would amplify once to get back to the herd size you wanted. But,
Yeah, I think in fisheries management, you know, wildlife management, they have sort of maximum reproductive excess kind of models.
yeah. But my cost measure is the time, the number of generations, and I'm not counting the cost of feed or anything like that.
Do you have any hints that sometimes it's good to sort of create small pools and to have breeding within them and then link them together and make bigger pools, or is everything happening in one? Well, the farmer has complete control.
Yeah.
Maybe the question is not right.
Well, no, the question is fine. I mean, you might divide the stock into two classes and try and improve each one separately and then somehow combine the results.
Right,
Can't do
dividing
better.
worker, yeah.
This is-
But this is a case where the effective fitness that the farmer is putting on is just additive. It's a sum of the effect. You're using the total number.
Additive is the wrong word there. You're adding up the number of genes that are right, and then you're thresholding it.
No, I agree.
With,
No, I
yeah.
agree.
Yeah.
Okay, that's-
So it's nothing
it's
like
non-linear.
small additive
There are no
effects in the,
selection coefficients in this model.
No, yeah.
Yeah.
It's a-
yeah,
The quantity which you're taking before you put this nonlinear function on it is additive.
yes,
And that's why it pays to keep the whole population mixed together. If that quantity was not additive, then it pays to break up population in some sort
I
of
see. Okay.
yeah. So it's the payoff function is a function of the sum of the individual contributions.
particularly if monotonic in order.
Okay, so I mean, basically what I'm doing is I'm taking two sort of, not absurd, but easily criticized things and trying to improve them slightly and make them less objectionable. So the next one I want to deal with is treatment of evolution as a random walk. And this was done by Stephen Jay Gould in a book called Full House. And he modeled evolution as a random walk on a line. So think of a species that's taking a random walk on a line, and the ordinate that the species is walking along is some sort of complexity. Again, I'm not imputing to nature any goal, but you might be interested in more complex organisms and find them more interesting than simple organisms. And so we might be interested in analyzing the origin of complexity. The idea is if you're sitting at that middle dot there, you take a walk to the left that's decreasing complexity with probability p, and you take a step to the right at each time step with, of course, with probability 1 minus p, you gain a unit of complexity. And Gould assumed that the two probabilities were equally balanced. Okay, so you're equally likely to become less complex through forgetting some evolutionary improvement, or it turned out not to be an improvement, so you regressed to your original state, and you're equally likely to gain a unit of complexity. And of course, he also pointed out that there's a limit to how uncomplicated you can be. If you start at the origin, you're going to make a random walk, and so after a number of steps of time, you'll have a binomial distribution, but you're not allowed to have negative complexity. There's a limit to how little complexity you can have and still be alive. So he said, okay, there's a wall at the left, and you're constrained to stay to the right of it. And then, of course, what happens is the left half of the negative part of the normal distribution wraps over and essentially doubles the positive part, and at some later time, the distribution will be like this. But at any given time, most of your walkers are within a few standard deviations of the origin, and a few standard deviations standard deviations is proportional to the square root of the time, and so at time t, most of the species will be very simple. They'll be within square root of t of the origin, and he pointed out that this is observed in practice, that most species are cyanobacteria, or very simple one-celled things. And of course, there are some walkers that manage to get very far out, but they're, as a fraction of the number of species, they're very tiny. Okay. Now, of course, this model is highly objectionable because it's absolutely sensitive to this assumption that you're equally likely to go in either direction. If you're slightly more likely to go to the right than to the left, and the whole population sweeps out triumphantly to the right, making linear progress with time. Okay. Completely different qualitative behavior. If there's an even slight bias to the left, then there's an equilibrium distribution, which is the exponential. It's the embedded Markov process in the single server queue, and the queue length just declines exponentially. And as time goes to infinity, the whole population approaches that fixed distribution in the limit. In the other two cases, there's no limiting distribution. Everything is eventually extremely spread out. Okay. So I want to try and find a modification of this scenario in which there's something like slowness of progress that he described, but it's not sensitive to the individual parameters. And what I'm using for this is a random walk in a random environment. So there are two types of randomness going on here. First, there will be a random process that creates an environment in a random way, and then our species will take a random walk in that environment, and the environment remains fixed once it's been generated. Okay. So here's the model for the random environment. Again, it's already been described today. It's going to be the infinite tree of a branching process. This will be a single species branching process. So we'll be able to compute the extinction probability even with pencil and paper. The model will be very simple. It's a tree, so all I need to describe is the random variable that's the number of offspring of a given individual. Okay. And so I'll say each individual has 2 children with probability A, and no children at all with probability 1 minus A. Okay. And so the average number of children will be 2A. If that's strictly greater than 1, then with positive probability, the population will expand exponentially. If it's strictly less than 1, then with probability 1, everything dies out. And if it's exactly equal to 1, if A is a half, then that's the critical case. And the probability of dying out is again 1, but now it happens linearly rather than exponentially fast. Okay. And of course, since we want to be able to talk about large amounts of progress, I'm going to always condition on the event that the tree is infinite. Okay, so it doesn't become extinct. Okay. In the critical case, that's conditioning on an event of probability 0, but it still gives a very well-defined tree. And in fact, what it looks like is there's a spine, and dangling off each node in the spine is a little tree which is finite. But there's only one path that goes down to infinity in this case. So here it is in pictures. You're sitting at the black node with probability 1 minus a, you have no children, and with probability a, you have 2 children. I've drawn your parent there too. Okay, and now after this tree has been created, we come in and make a random walk in it. And so now I again have to have that parameter p that describes whether you regress or make progress. Now, regressing was going to the left before, now it's going up in the tree, because as a computer scientist, I put roots of trees at the top and leaves at the bottom. That's obvious, isn't it? So you will ascend with probability p, the same as before. You regress with probability p. If you're at a leaf, you have no children, then you ascend with probability p, and you stay with probability 1 minus p. And if you have 2 children, then you go to either of them with probability half if you don't ascend, given that you don't ascend. So there it is in pictures. Okay, so Gould's case is a equals 1. Everybody has 2 children. Of course, now you get an infinite tree rather than a line, but nothing ever stops you. So P in his situation is just the same as P here. It's just that we've turned things 90 degrees and expanded to a tree. The level you're on corresponds to how far you've moved horizontally in his situation. I found one other paper in the literature that examines this model, which is due to Harry Keston. And he actually studies quite a large class of processes, but it has an intersection of 1 with the situation I'm considering. And that's where a equals a half, so it's the critical case in generating the tree. And the tree looks like this. There's a spine, and little trees dangling off. And p equals a third, and what that means is if you have 2 children, you're equally likely to go either of the 3 possible ways: up, left, down to the right, down to the left. Okay, and they're all equally likely. That's the common theme of all the things he does. Okay, but I want to be able to play with the parameter p and also with the parameter a, so that I can talk about other things that correspond to what Gould was doing.
What do you mean to go up on the tree?
To go up means you move to your parent.
Yeah, but
So you think of it as undoing the last mutation. Or actually, Gould was thinking in terms of speciation events. So you decide that you're not as good as your parent species, and so you just go extinct, and that line returns to its parent. That line of descent terminates with you. And
this means to go to, okay.
yeah. Why that should be equally likely as going down, I don't know. But, okay, so the conclusion that Keston came to is that at time t, most walkers are above the level cube root of t. So you're even slower than in Gould's case. I'll point out later that this is a completely different phenomenon. The phenomenon here is what I call trapping. When you descend into one of these little trees, you have to work your way out, and if p is greater than a third, you have a bias downward, and so it takes a lot of time to actually climb out. The first few steps, you go down, down, down. It was great, and then you have to climb out of all of these evolutionary dead ends before you get to make further progress. So let's sort of switch processes a little bit. The first time I enter the trap, at that point in time, I'll throw the coins that determine what the trap looks like. Okay. And then I'll take the random number of steps that I need to enter the trap and come back out again. That's a random variable. That random number of steps is finite with probability 1, but it has an infinite expectation for certain values of the parameters, like Keston's. Okay, and these random variables they're finite with probability 1, have infinite expectation, are often glossed over in probability courses as being pathological, but they come up all the time. If we flip a fair coin, and I pay you $1 when I win, and you pay me $1 when I win. Suppose the first coin comes up heads, and so I pay you $1. Okay. If we go on flipping, eventually we'll be even again, sooner or later. We're bound to return to the origin, but the expected time to do that is infinite. Furthermore, if we play this game until returning to the origin, if we play it for n flips, some huge number n, and we ask how many times did we return to the origin, it's not proportional to n. It's proportional to the square root of n. Okay. And this is exactly the same sort of thing. During your first visit to a trap, if you regard the trap as also being a random variable, the number of time steps it's going to take you to re-emerge and get back to where you can make progress is going to be one of these random variables that has an infinite expectation. And so to go down a long distance, it will take, to go down a distance d, it will take roughly d cubed time steps, because you'll spend all the time in these traps.
But I guess the heuristics would suggest that you have t to the alpha, where alpha is a function of p. Or is that the wrong?
That's right. It'll be a function of p and a. In fact, he proved much more than this. He proved that the random variable of the amount of progress you've made divided by cube root of t converges to a distribution. And I don't have anything nearly that precise, but I can show that trapping occurs if p is less than a certain threshold, which depends on a. And so here you see, Keston's situation is this point. And it is another of these knife edges. Gould's point is this point. Looking at.
Trapping means you will never get out of some.
It means it will take you a long time to get out.
Long in terms of?
If you make these steps of progress, it will take you a number of steps more than linear in d. If you go to descend d levels.
Go with finite rate.
Why cannot all these be by expected values?
Because the expected value is infinite.
Yeah.
That's the thing. To return to the starting state in the coin flipping game, once I'm down 1, I will eventually return, but it'll take the expected time to return is infinite. And what that means is to return n times, I'll need n squared flips to see n returns to the origin. It's not that there's a certain amount of time needed for each return. Yeah, that would be infinite. But still, you are going to see returns, each occurring with some frequency. And the question is, what's the frequency, the rate at which they return? And it's just not proportional to n anymore, or proportional to t. So if you're in this region at the very bottom, trapping will occur, and to descend these steps in the tree, you will need to take an amount of time that grows as d to some power greater than 1.
Just to get a biological understanding of the trapping, is it something like if I evolve into a whale, would I have to evolve back into, I don't know, whatever land animal whales came from in order to make any further?
No, I don't think. I find it very difficult to get a completely consistent view of what's going on here. So Gould identified a walker with a species, but I don't think the idea is if you evolve into a whale, then you have to unevolve. But everybody talks about evolutionary dead ends. So what happens is that the offspring species turns out to be less fit than the parent species, and so it takes time for the offspring to stop competing with its parent, and that slows down the parent's ability to evolve.
So, I mean, there is an analogy where you don't have to go to species. That if you say that if you're on a local fitness maximum, and it takes K mutations to get away from that, to get to a higher point, you have to go through a valley, and you need K steps. So then the probability of doing that is, loosely speaking, mutation rate to the K. Okay? If you ask what is the chances of getting stuck on a peak, which has K mutations that you need to do better than that, is also some function to some number to the K, then you get exactly this behavior. So it's
Okay, so this trapping is a completely different phenomenon. Well, let me give the quantitative result. So as you approach the bottom line in this picture, as long as you stay away from A being close to 1, so that there are very few dead ends, as if P goes to 0, so you have a very strong forward urge, the trapping becomes stronger and stronger. I mean, with Gould's phenomenon, he was sitting at the knife edge of P equals a half. If he moved even a little bit below P, things got better. A half P, things got better. Here, as you go below this top boundary here, which starts out as a third, as you go below it, things get worse and worse. Okay, so Gould is up there, things get better. Things get worse as you go up from here. Okay. In this region, things get worse as you go down. And the next slide is just an upper bound to the exponent of t. Of course, if you flip it around, you get a lower bound to the exponent of the distance. Okay. And so you can see, as long as a is bounded away from 1, the numerator is just some bounded thing, and the denominator, if p goes to 0, under those circumstances, the denominator is blowing up, and that's forcing theta to be small. It takes longer and longer to make progress. So that's just saying what I just said, so thank you.
More questions for Nick?
So I guess there's a
Yeah.
comment which I think in some ways makes this even more interesting. If you ask now, I have a very large population, so some individuals are picking up mutations and going in directions that are going to be dead ends. Some may be luckier and pick up mutations that don't go to dead ends. And then there's a question of what is the dynamics of this tree and when do you tend to get stuck when you have a very large population that's competing with each other. And that, I think, also can come back to your earlier question, to your earlier part, is that, of course, depends on how much benefit there is for being one level further up the tree. And there's an interesting optimization question, I think, there. If you look at a big population which is maintaining some diversity so it doesn't get stuck too easily, but it's still eventually going to go up the tree. It's not an easy one.
Yeah. So, I mean, you might try and amalgamate it into one single walk in a random environment where the walker now represents the whole biome, all species that are competing with one another, and yeah, that's not evolution.
This is the dynamically generated diversity staying enough there to be able to keep going up the tree, or being very unlikely to get stuck, and that. But I think trying to understand that even in this kind of relatively simple model is an interesting challenge.
Yeah. So I mean. The model, even as Gould stated, it has multiple walkers, but they're non-interacting walkers. They're not competing with one another, and that's completely lost in this model. I agree. Somebody.
So in the first part of your talk, you had this inequality, the number of generations of these C times the square root of E.
Yeah.
What's the, what does that really mean? Does that mean the expected number of generations is greater than that, or does it mean with high probability the number of generations is at least that?
It means both, but with different values of C, of course. If the population is large, and what you want to do is get all of the fractions to be at most epsilon, the fractions of bad genes to be at most epsilon, then you can work out what the C will be as a function of fecundity and epsilon. Okay. Both as an upper bound and a lower bound, so you can get tight bounds. If you have to play one of these endgames, then what endgame you play, what strategy you use, depends upon exactly what it is that you're trying to control. And I only did enough work to show that the contribution of the endgame is no larger than the contribution of the main term. So the upper bound, you get the same form of upper bound, just with a larger value of C.
Yeah, it would be very interesting to contrast this work with Winnow, because there, the only thing you would need is that every genome is above a certain threshold. The good guys are above a certain threshold. You want to clean it out completely and put all of the ones sort of in the same chromosome and make them all identical. So it's very interesting what you did. I mean, and then also to contrast it to the other regime.
Yeah, but I mean the last step is where the population size comes into it.
He has a different goal, but for this goal, what he does is optimal.
Yeah. There was a
David, what?
Yeah, so just a math comment. Is that there's been a lot of work in math probability on speed of biased random walks on trees,
yes.
although they're using a slightly different model from what you're doing, where that instead of fixing a parameter p as a chance of going to the parent, it's sort of p over p plus the number of children. So they have a different model.
Yeah.
There's sort of very expensive work.
Yeah, I picked the model so that I could get Gould's theory as a special case, and contrast with it, and also so that I could get Keston's result as a special case.
One more?
Yeah, so omniscience versus omnipotence.
Yeah.
Your farmer is a very powerful person.
Yeah.
Suppose all you get to do is design inhibitors on viral populations, and you can't pick individuals, but you can pick across distributions of them. How much of this goes forward?
Well, if I have a very smart virus that can read the genome and take a threshold function, add and take a threshold function, then you can do the whole thing. But I think it is an interesting. If you had additive contributions and then you did some Hills thing, which wasn't an exact threshold but an approximation to it, then I think it would be interesting to see how well you could do there. There's a very interesting result by Les Valiant on how you can compute medians or threshold functions in the Boolean setting if all you can do is take a majority of three things, or a median of three things. And it turns out that you can bootstrap this very simple approximate thresholding into a very exact threshold.
So things are going fantastically well because we are going out of the schedule like crazy, which is fine. So that's